Hey guys, just an update with mentorship. You should have received an email from me earlier this afternoon if you applied with your mentor-mentee groups. If you haven't seen it in your email and have multiple emails, it's sent to the email that you used to apply, so you can check that for your matchups. I do ask that please mentors reach out to your mentees as soon as possible because I think it'd be really beneficial if like communication was started before the career fair in case people have questions about the career fair, whether they're going to be attending to apply and get internships or just general information. And if you haven't already noticed, if you are a mentor or a mentee, you have a new role in Discord that we manually assigned you to that allows you to see the new mentorship Discord channel. So look out for announcements on there. Thanks.
And we have pizza, so I'm not going to present until everyone's gotten their pizza. Okay, we're going to get started. I think everyone's gotten pizza. So. Yeah, this is intro to networking. It's mainly for people who know nothing about networking, but I'm also going to target some people who maybe have basic concepts about IP addresses and ports and things like that, but aren't really super confident with their knowledge on it. So I'm going to go into some details on that, but it's mainly going to be conceptual at first, understand conceptually what goes on in a computer network or in networks in general. And then we're going to go into a couple of examples, and I'm also going to be drawing diagrams on here because that's way easier than using diagram pictures on my presentation. So. First of all, I hope we all know what a network is, but just to be clear, it is any collection of peers or objects, nodes, people, computers that are able to communicate with each other. So this room is a network because we all are able to communicate with anyone else in the room, basically. And we do that with our voices, and we identify who we're talking to by looking at them, right? And these are all trivial things, but in computer networks, because everything you do has to be programmed and deliberate, this is an important thing to understand, right? So it's not like a given that because you have a bunch of computers and a bunch of hardware that the computers can talk to each other. There's a huge level of logic that's going on behind the scenes there that you're not seeing, and that's what we're going to get into now. First of all, to lay out some terminology, when I say hosts, I'm going to be talking about PCs, laptops, servers, cameras, printers, anything that is a member on the network and is communicating with other members on the network, right? And it used to just be PCs and servers, but now lots of things can be hosts, anything that can connect, basically, that can make an internet connection. Interfaces are ports on a host, and so that's the actual device that lets the host communicate on a network. And links are the actual connections that you use to connect interfaces to each other, right? So you might have two computers in a really simple network where you just have, each computer has one interface and then there's a link between them and they talk to each other like that. That's the simplest kind of network. And then lastly, when I say middleware, I'm talking about things like switches, routers, firewalls. These are also hosts, but they're hosts that sit between other hosts and facilitate the movement of traffic over the network. And you're going to understand what that means later on when I actually go into what switches and routers are if you don't know what those are already. But they're hosts, and I'm calling them middleware because they have a specific purpose that are distinct from other hosts. So the first thing that is important to understand is that in order for computers to communicate with each other, they need to have some kind of physical pathway to get to each other, right? There's lots of complicated stuff going on behind the scenes that you're not seeing, but what is very easy to recognize is that if that computer on that table is going to talk to this computer on this table, there has to be some kind of cable, some kind of wireless means. There has to be some kind of connection between them. We're just going to focus on cable, wired connections. We're not going to talk about wireless stuff because that's kind of out of scope, but this is the first layer of our network, right? And this is the most important one. It's how you actually communicate. And so the question now is, okay, we know that we have to connect the hosts in order for them to talk to each other, but how do we connect them? Because you could, the first intuition is like, if I want all these computers in this room, which there's a lot of, if I want them to be able to talk to each other, well, take computer A, plug it into computer B. Take computer A, plug it into computer C. Take C, plug it into B, right? So if you have all these guys and you want them to be able to talk to each other, you do that, right? So that's kind of horrible because you can imagine with big networks, that's not possible. Like there's just way too many computers. Even just in this room, that would be like insane if you had to connect them all. Well, okay, so maybe we don't connect them all to each other like that, but what if instead we have another host, right? We're going to call this right now a switch. And we connect all of these hosts to the switch. And then the switch kind of acts as a broker between all of the hosts, right? That's a better way to do things, right? And in the second point, I'm saying connect them to a central location. And then in the third, I'm saying connect to a switch. Now, the way that this could work is it could be like stupid and it could just take what this guy is saying. Like maybe this guy, we'll call him A. He wants to talk to B. The way that old, they're called hubs. The way that hubs used to work is you would send traffic to this guy, right? And we'll call this guy C, right? And then he would go, oh, okay, A wants to talk to B. Sure. I'll just send it to everyone. And then if one of the people that I sent it to happens to be B, then he'll have the message and then he can respond to A. And then I'll do the same thing. I'll just tell everyone, hey, B wants to talk to A. Whichever one you use A, here you go, right? But that's kind of horrible as well because, if you know where A and B are, if C has knowledge of where they are on its interfaces, then it can be more intelligent about how it does that. That's what a switch does. And we're not going to go into the magic of how it works, but how a switch works is, A wants to talk to B. C knows that A and B are connected to these interfaces here. So C will take the packet from A and send it to B directly. There's no transmission to all the hosts. It just intelligently knows to get the packet from A to B. When I say packet, I realize that I didn't specify this before, but when I say packet, I'm talking about just data. Like a packet is a unit of information in a network, and that's what I'm going to be referring to when I'm talking about like data transmission. I'm going to be saying packets are getting sent over the network, right? Okay, so that's what the second layer is. The second layer is concerned with, we have the hosts and we have these connection things, right? But how do we make a network out of those? Well, that's what layer 2 is. That's what the switch does that I just showed you. It facilitates communication between the hosts instead of just having them connect to each other stupidly. And that's C whiteboard is what's on there right now. Now, networks aren't a particularly difficult problem to solve on a single level, right? When you make one network, I've just explained how that works. And conceptually, that's pretty easy, right? But the problem comes when, I have a network here, right? But then, maybe in the next room over, I have a network over here as well. And so these guys are separate networks. They're all talking to each other. They're having a good time. But then it's like, okay, that's fine. This guy wants to talk to A. B wants to talk to A. But A is over here, and there's no link between them, right? You might say, okay, well, that's fine. Just connect the switches together, right? Just make a mega switch, right? But that doesn't work either because it's the same problem we were having when we just connected all the hosts together. It gets messy. And we want another structure that we could use to facilitate communication, not between hosts, but between networks. And that's what the third layer is. So layer 1, deals with hosts communicating. Layer 2 deals with managing all these hosts. It makes a network. Layer 3 deals with having networks communicate between each other. Okay. Are there any questions up to this point? Because I'm kind of blazing through this first part. Any questions at all?
Is there any like latency issues with like, you know, like internet, like different networks?
Mm-hmm.
Is that a big?
It's not usually an issue. Like the hardware can be made very, very fast. The problem is usually the physical limitations of the mediums you're using. So like if you have a really slow internet connection, you might be using copper wire, or you might be using some kind of like medium that's like really terrible, or like Wi-Fi maybe. And then for another example, like if you're trying to connect to somewhere in Asia from here, it doesn't matter how complicated and like high tech and perfect your mediums are. There's a physical limitation to how fast electrons and light can like physically get to Asia, you know? So, but usually no, like these switches and like all these things, usually the latency is like really, really low, like less than 1/10 of a millisecond. So, any other questions? Okay. Yes. Yeah, I'm not going to talk about spanning tree protocol. That's too complicated for this one. So, okay, before I move on to the other layers, I want to establish some constructs that exist in these first layers. Now, the constructs for layer 1, we've already discussed. That involves interfaces and links, okay? But layer 2 has its own terminology, you could say, and layer 2 has a thing called a MAC address, okay? And a MAC address is, all right, layer 2, MAC. So, wait, does address have 2 Ds? Yeah. It does? So, a MAC address, we're just going to like say that the letters are the MAC addresses, but it's essentially a unique identifier that the machine gets when it's built. So when they're building the machine, they hard code this into the machine. It's called the MAC address, and it uniquely identifies the machine. And that's what allows switches to, know who they're talking to. Like, because if you don't have a name, then switch doesn't know who you are, right? And now you might say, oh yeah, well, these guys are on interfaces. They don't need names. You just need to know the interfaces they're on. It's like, okay, well, the problem with that is that now they cannot leave that interface. If they do, then the switch no longer knows who they are. So we give them a MAC address, and then we say, we don't care where you're plugged into. Like, this identifies you, and the switch uses that to, send packets between A and B. On layer 3, we have a thing called an IP address. And you guys have probably heard about both of these. IP address is probably the most because it's like kind of a pop culture thing. But what an IP address does is it's a number that we assign to these machines. So we're giving them a second identification, right? And that's the number that we use to identify them across networks. So A and B can be used to communicate within a single network, but 1 and 2 and 3 can be used to communicate between networks. The reason that we even have this separate thing called an IP address is because, you might have A, but this is A, and maybe A has an IP address of 4, right? So if A wanted to talk to A, you can't say, hey, send A to A, because when you send that to the switch, it's going to go, okay, here you go, A, you're A. And then you're going to go, no, I want to talk to 4, okay? Then this will get sent. I'm not talking about how it's getting sent right now from this network to the other. We don't actually connect the switches together. But this packet gets sent here, and the IP address lets us differentiate. So hardware, MAC address conflicts aren't a problem. They shouldn't be. Like, you shouldn't have MAC addresses that conflict. In theory, they're completely unique everywhere, but it's still possible. Any questions? On Zoom. Why would a MAC address be used? It looks like an IP address could be used either way. Yeah, so the reason that we use the MAC address is because IP addresses aren't givens when you have a machine. Like, when you buy a machine, it's not like it has a hard-coded IP address on it. So that gets assigned to you when you join the network. Like, you'll join in and you'll go like, hey, I'm here, I'm plugged in, and then you can either do it manually or you can there's like protocols that let you do it automatically, but you get assigned this when you join the network. And maybe if A goes to another network, it's going to get assigned a different IP, like 3 or something. But there's utility in being able to have a disconnect between the physical identification of the machine and the logical identification of a machine on a network, if that makes sense. You can change the IP address around and everything. That makes sense? Okay, good. Yeah, it's really useful to have it. Yeah, so I think before we move on to the next one more thing, right? So we have our switches, we have our hosts, and we have our networks. Great. And we know that the networks are able to communicate with each other using IP addresses, right? But right now I'm just saying that they're doing it through magic, but it's not through magic, right? What you have is you have another guy. We'll call this guy R1. And then you'll have another guy on this network, R2. These guys are hosts. They're middleware, right? Because they're being used to facilitate communication, but they're hosts, okay? And what they do is, and I need to actually make these numbers more complicated. Okay, because that's important, we need more information. So what routers do is they facilitate inter-network communication, okay? And by the way, that's not a coincidence, inter-network, internet. That's why it's called the internet, right? Because it's inter-network, okay? Yeah, I just learned that today when I was like researching, but basically the routers are the things that actually facilitate the inter-network communication. This is how that works. So computer A wants to talk to computer, we're not gonna use the letters anymore, we're gonna use the IP addresses because we're talking about between networks. 1.3 wants to talk to 2.3, okay? And it has a table on its own computer, right? So we're going to call this A's routing table. By the way, routing is the term that you use when you're talking about how traffic is routed between networks. So we call it a routing table. So A's routing table. So A knows that if it wants to communicate with anything that's on one dot anything, okay, I'm using an asterisk to signify that that could be anything. It knows that it just has to send it out on this interface. So we'll call it interface 1, right? And this is interface 1. It sends it out on its own interface, and then it knows that the switch is going to take care of things and then get the packet, get the response back that it's expecting from the person it's communicating with. So in a layer 2 network, that's all you have. You're just sending stuff out in the interface and expecting it to come back, right? But now if you want to talk to 2 point something, right? Anything on the 2 network, which is over there, that's a problem. It's not on this network. So what you do is you send it to not an interface, but you send it to a host, R1. You say, okay, I know that this network is like nowhere to be found, but I know a guy who can get me there, R1. So I'm going to send my packet to R1 and tell R1, hey, going to go to the switch. Switch is going to take the R1. Hey, R1. 1.3 wants to go to 2.3. Can you make that happen for me, please? And R1 says, yeah, sure, I can do that. And then it sends the packet along to R2 because R1 has its own routing table. And the important thing about R1 is that it has more than one interface, okay? Now, R1 has an interface on the one network, but it also has an interface on the two network. So when you send it to R1 on his routing table is going to say, okay, I know that the one network is on interface 1. I'm going to call it I1. I1, I2. I know that the one network is on I1. I know that the two network is on I2. Good. So it doesn't have to do any layer 3 stuff. It knows that there's a physical interface it can send the packet out on. This is a layer 2 concept, sending packets on interfaces, right? Here we sent it to get to network 2, we had to send it to a IP address, R1, right? Or actually, we should give this guy an IP address. He doesn't have one, so we'll say that he's 1.10. So we knew that, you know, we had to send it to an IP address, but that's not how hosts communicate with each other. They communicate with interfaces, with MAC addresses, right? Like, I know 1 is on the interface 1, so I send it on there. 2 is on this IP address. That's abstract. So, you know, you're pushing the problem along of where the packet is going to go to someone else. But then this guy has a solution because he has a physical interface, and so, you know, he sends it to R2, and the same game gets played there. R2 has its own 2 interfaces, and then he's able to say, oh, yeah, I know where to get that. He sends it along the switch. The switch figures out, oh, I know where 2.3 is, sends it to 2.3, and all the way back again. And that's how we communicate between networks. Questions? Yeah.
Is every router like connected to each other? Or does a router go to one router to then go to like a third, for example?
Yes. Yes. I'm not showing it here, but you might have you can have as many routers as you want between these two, right?
So routers will go through other routers to get to like the final destination.
Yes. And it's that same game of sending stuff over interfaces, over layer 2 networks. So layer 3 is just a strategy for figure it out later and figuring out who's going to figure it out later. Like, hey, I don't know where this network is. That's fine. This guy knows where it is. Hey, I don't know where it is either. That's fine. This guy knows where it is. You know, over and over and over again.
So it actually like figures out.
Yes. Yeah, exactly. As a side note, you all probably know that Facebook went down not that long ago, for a long time. And it was because their routers, these tables in their routers got wiped, basically. Like, there are protocols that routers use to communicate between each other so that you don't have to go in and hard code these mappings, because that would be very labor intensive if people had to do that manually, right? So there's protocols that let you do it automatically, and those stopped working. And so they lost all the routes and their entire network went down. So yeah, that's like side note. Now you know a little bit more about how that happened. Ben can tell you more about it as well, because he's the real networking pro here. I'm just the educator. So now I hope we have an understanding of how networks work, but so far we've just been talking about sending like abstract data between them. And that kind of implies that there's only one application on the machine, right? So you send out a packet, it comes back to the machine, right? What if you want to have multiple machines? Or what if you want to have multiple applications? Maybe the kinds of communications you're having, like, you know, people have single conversations between each other, but computers can have multiple conversations all at once. You can have for example, on your computer, you probably have Zoom open, you have a web browser open, you have Discord open. All these applications are all talking over the internet at the same time. And so in order to, with this model, we can't do that. You can only have a single application listening on a host because there's no like differentiation between applications. It's not too difficult to do that. Conceptually, you assign a port to a connection, and then an application uses that port. And I'm going to show what that means. So we have our host, right? And we're not going to consider the networking stuff right now. We're concerned right now with how you have multiple applications. So this is host A. This is host B. Oh, is it that bad? Make it nice and big. So we have two hosts, and they're communicating with each other, right? What we're concerned with right now is how to represent different applications. What's going on here, this could be, you're going through a router, you're going through a switch. Maybe you actually are just connected directly to B, but that's not important for this, right? So A has, if like stuff isn't easy to see, then just interrupt me because that's kind of defeats the point if I'm like drawing for myself. But A might have, program 1, program 2, program 3, right? And B might have, let's just say B has 2 programs, program 1 and program 2. So we've established that there's multiple applications and each of them can communicate at the same time. But not only that, each of the applications should be able to have multiple connections for itself. Like, for example, a web browser can connect you to multiple websites at the same time. It would be stupid if you could only use one website at a time in your web browser. So this guy might have, let's go with simple port number. Let's say this is port 1, 2, 3. And this guy has 4, and this guy has 5 and 6. Okay. On a given machine, these listening ports is what they're called, are unique and they cannot conflict with each other because that defeats the purpose. Ports are used to identify connections between applications. So they have to be unique, at least on the source. P1 on B might have 1 and 2, and then P2 has 3, right? They conflict, but because they're on different hosts, it doesn't matter. It's just used to identify connections for applications on this host. Now, the way that ports work, the way that they let you communicate between applications is each of these guys is going to keep track of, for a given connection, right? So we'll call this like a connection table. Right. So A is going to have its own connection table where it keeps track of a process. So P1 has a connection on port 1 with B on port 2 of P, right? And we're actually going to say, we're not going to worry about the association between programs and ports. We're going to assume that if you know the host and the port, that you figure out what program it goes to. But essentially, A keeps track of its connections by keeping track of the port on itself, the identifier could be an IP address, and it usually always is an IP address of the second machine, and then the port on that machine, right? And it's that simple. Like, and then B will do the same thing. So B will have its own connection table. Where it says, okay, I know that I have a connection, and it's on port 2, and it's on A's port 1. And so ports let us route information between applications on 2 different hosts. Any questions? Okay, so ports are a layer 4 concept, just to be clear, if you care about the layers. Layer 4 is concerned with ports. Layer 5 is concerned with the actual application and how the information goes from the application to the port. Okay. Yes.
How does programming work on A and the two go to port on B?
That's a good question. It depends on what you're doing. For most things, you have standards. You have basically like web traffic will always be on port 80, encrypted web traffic will always be on port 443. And if you know the IP address of a machine, for example, like I don't know how familiar everyone is with DNS, but you might do a DNS query to say, I know google.com is a thing. Where's the IP address for that? It'll say, oh yeah, here's the IP address. And you're like, okay, great. I have the IP address. Now, where's the web server? We don't have protocols in place that tell you where the web server is. You just assume that it's on port 443. So you're like, okay, I have the IP address. Now, how do I get to the web server? It's probably on 443. And then you do that and it works every time because no one else uses different ports unless you know what you're doing and you do that manually. So does that answer your question? Any more questions? Because this is the end of the stack. And we're gonna start doing an example.
I'm assuming that these ports are like virtual, like they're not physical.
Yes, yeah. They are virtual, they're numbers that
Are
are,
there like cases where there are computers that use physical ports for this, or is it always?
well, I don't think so. At least not in the same way. I mean, in the sense that you might have a number that identifies a device, yeah, but it's kind of like separate concepts at that point. Yeah. Any other questions? All. Okay. So I think the most important thing to take away from this is that the whole point of doing layering like this is so that we can worry about one problem at a time without having to worry about the immense complexity that underlies that. Like through everything we've been talking about, it's important to understand as well that this is all due to the hard work of computer engineers and electrical engineers that are dealing with very, very complicated things that I don't understand, right? But I'm still able to write a program and I'm still able to communicate over networks because of these layers separating the complexity of the problem up, So to recap real quick and to give you some actual concrete terms and, protocols to go with this, all these layers that I just described to you is called the OSI model. And there's actually 7 layers. And the 5th layer, I've just crunched layer 7, 6, and 5 into the 5th layer because it's not important for this talk. But this is like the technical official term for what we just went over. Layer 5 is the layer where the information is generated that you want to communicate. So if you're trying to text someone, layer 5 is when you type in the text and you hit send, the application will maybe encode that information and then pass it on to layer 4. Layer 4 is concerned with making sure that it can get from one program on one host to another program on the other host, right? Layer 3 is concerned with actually getting the data between the hosts, between networks, which could be the same network, but is usually different networks. And then layer 2 is concerned with, actually facilitating communication between hosts with switches, which is what they're physically plugged into. That's the actual transported data. And then layer 1 is, how do we physically send the information out, right? Like, I'm not a pro on, engineering or anything, but, that's like what your modem does. That's what like fiber optics are. There's lots of like very interesting stuff that goes on at this level. And then actually to backtrack real quick, some examples of what are considered layer 5 concepts are things like HTTPS, which is web traffic, SSH, secure shell, right? Layer 4, these port numbers, you can have 2 different kinds of ports for the most part. You can have TCP ports, right? So this would be like, you would say 1 is a TCP port, 2 is also a TCP port. You can't have TCP communicating with UDP. It has to be the same on both places. And the difference between those is TCP is I think it's transmission control protocol. And then U is unigram data protocol. What is it? User data protocol. Datagram protocol. Yes. So the point is TCP is used for reliable connections where you care about, the order of your packets and things like that mattering. And you want to confirm that when you send the packet, it got to them and not just was sent out. UDP is just like, yeah, send the packet out. And like, if it gets there, then great. But I have no idea if it got there or not. But then we went over IP addresses roughly. IPv4 is what most things use. And that's an actual IP address instead of the fake ones I've been showing you. It would look something like 192.168.0.55. Yeah, that's what an IP address looks like. And then IPv6 addresses are ugly. I'm not showing them. And ICMP is not related, but that's the protocol that you use when you ping. I don't think that's a layer 3 protocol, is it? Okay, so ICMP is supposed to be in layer 4, so that was a blunder. But Ethernet, Ethernet frames and Ethernet, for that matter, MAC addresses, which is how you identify the interfaces, look something like this. It's like AA, BB, CC, BB, 27. Put numbers in there. It's 6 octets, right? Yeah. Okay, yeah. So Ethernet frames use hexadecimal, and then there's 6 octets, and IP uses 4, and it uses decimal numbers when you write them out. And then physical, I'm not even going to try to explain that. Some examples though are like fiber optics, modems, anything that has to do with actually translating the data that you're getting to something that can be transmitted. So now we're going to look at, we're going to do a quick example of the entire flow of traffic, breaking down each step when you connect to a website. So are there any questions before I do that? Yes. It all happens internally when you go to localhost. Yeah. Even when you go to so say that A has a request and he's like, hey, I want to go to 1.3. Well, he's 1.3, right? So that also won't go to the switch because he's smart enough to recognize in his own routing table that 1.3 is himself. So that wouldn't go out, that would go back to himself as well. Yeah. Do you have a question? Okay. Any more? Also, I'm erasing this to do the example, so you can get it in the recording. Okay. So let's set up a little network. So we're going to have this guy, and there's going to be a switch here. Let's say there's a router here, another router here, there's a switch here, and then there's finally a computer over here. And then we're gonna put this up. And then we're going to draw our links, do some labeling. This is host A, this guy is B, this is going to be switch 2, and this is R2. These guys, I'll just say that. I think I just want to reiterate again that it's important to remember that between each of these nodes, like for example, between A and S1, between S1 and R1, between R1 and 2, between any of them, there can be any number of middleware, essentially. There could even just be plain hosts that are acting as middleware. Like the point is that we're just concerning ourselves with the most important points in transmission, right? Like there could be, again, like when you're going over the actual internet, there's probably much more than just 2 routers that are directly connected. There's probably like, what, like 30, 40 routers, like big, really like beefy routers that are handling everyone's traffic all at once. But for the point of this, we're going to not consider those. So in our example, host A is going to want to connect to host B and retrieve a web page. So you could think of host B as being Google, Amazon, whatever you want. Like it's a website, and we know host B's IP address, and we know the port that we want to connect to on host B's IP address, right? And if you are concerned with the details, we know host B's IP address because we use DNS to get that, and we know his port because we're just assuming that that's the port for web traffic, which is usually always correct. So the flow of traffic would look something like this, right? Host A initiates a connection. So we'll say that, and let's actually look at some addresses. This is 1.1. They have IP addresses. This guy has a web server listening on port 443. And that should be okay. And then we'll name the interface as well. This is A1. This is S11. S12. R11. R12. Yes. Okay. So I've identified all of the hosts. I've identified each of the interfaces on them, with the exception of the switches. And I've identified A and B's IP address and the router's IP addresses. The switches don't get IP addresses because they don't do layer 3 networking. They are only concerned with moving layer 2 packets from computer to computer. Okay. So A, when you initiate a web connection, is going to say, hey, 1.10, I'm going to initiate a connection on 1.10 on port 57320. And the way that this is actually like similar to how it really works, when you initiate a connection to a web server, you come up with a random port that's greater than, I think, like 1024 and less than 65,000. And you just pick it. You're like, hey, computer, give me a port. And it gives you one, and then you use that for your connection. And host B is going to be listening 2.10. So host A is going to send out this packet with this request on it. Right? Maybe you send a GET, because if you're familiar with HTTP, that's how you request content. So he's going to look at his routing table right? So we're just gonna put it up here. He's gonna say, I know that one dot anything. We'll say 1.0. None of them have 1.0. This is how actual network IPs look roughly. So he says, I know that 1.0 is on A1. Like anything on the 1 dot something network can be sent out on A1 and it will get there. But I also know that, 2.0 is on it's on 1.1. I have to go through 1.1 to get there. Okay. So this, oh, and I forgot to put the destination. This is the source, but then you also need the destination. So this is 2.10.443. This is layer 5, and this is a combination of layer 4 and 3. Okay. So he sends out this packet on A1, but he's sending it to 1.1. He wants it to get to 1.1. So he sends it out on S1, and then S1 gets it to R1. R1 looks at the packet and says, oh, you want to get it to 2.10? Yeah, I know how to get it there. I have an interface here. It has its own table. Right? It has its own table where it knows that 1.1 is on R11 and 2.0, 1.0, 2.0 is on R12, right? Those are the names of the interfaces, by the way. I don't know if you can see them too well, but this is R11, this is R12, okay? So it goes, it gets the packet, and then it says, oh yeah, you want to send it to 2.10? Well, I know that all of the 2 IP addresses are on interface 1.2, so I'm going to send it there, right? R2 receives the packet, and he knows that, yeah, hey, that's my network. So if I send it out on my interface R22, it'll get to where it wants to go. So he sends it on R22, S2, knowing how to get packets to where they need to go on this local network, sends it to B, and then B receives the packet, right? And B does the same thing to get the packet back to A. It has the same table in reverse. And just to be clear about what that looks like, it's going to look something like this. It's going to look like, I know that 2.0 is on B1, 1.0 has to be accessed through 2.1. Okay, so B will repeat the same thing in reverse to get it back to A. And that's, I've kind of ignored how layer 2 plays into this because it makes the problem a lot more complicated. But that's how routing of data works from layer 5 and 3, just looking at those top 3 layers, right? And so that's a kind of a detailed explanation of it. But if I were to go into my computer and just do that, no, and then we go up, right? You can see there's the IP address of Google. Oh my God, there's so much crap though. So you can see when I do the request to Google, it identifies Google's IP address. It identifies the port, right? And Google similarly knows my IP address, 1.10, and the port that I initially started with, 57320. Yeah. And if you wanted to see what this table actually looks like, I don't remember, Jeff, do you know the command for that? To get the, route. Yeah, so that's the table on my computer that is actually doing the routing, like making the routing decisions essentially. So in my table here, I said that 2.0 was accessible on 1.1, but the reality is that you don't know that 2.0 is accessible on 1.1. You can't have every network in the world on your computer. So you just have one, and you call it default. It's identified with, how do you show the numbers? Huh? How do you show it like just the numbers instead of it saying default? Well, yeah. So default is usually written as 0.0.0.0. That's called a wildcard address. And if you see that, it basically means like, you know, that's a catch-all, like in a routing table. Yeah. So that's an example of how I reach the internet. Everything will go via this router, which is like probably that one right there on this device. So the layer 2 is the device right here. Similarly, you guys probably have an IP address on this network here. Forget the /16, that doesn't matter that much. You guys probably have an IP address that looks like that. And if I want to talk to one of you guys, then my routing table tells me that I can reach you guys, not via anything. I just send it out on the device and I can reach you guys like that because you're connected to the same switch as me, which happens to be a Wi-Fi router in this case. So it's not too hard to actually see. And if you wanted to see, there's a similar table that exists for do that. Yeah. Oh. So this one right here, the routing table I had showed you before, that was for layer 3 routing. This is the table that actually exists that tells your computer the associated MAC address that goes with an IP address, right? So when you do send that packet out on a switch, because you know that the person you're talking to is on the switch with you, that's fine, but you're still talking to them in terms of an IP address. Like you don't say when someone's on the local network, just because they're on the local network, hey, I'm gonna use your MAC address to talk to you. It's like, no, you still use the IP address, but you just have a table that maps them together so that you don't have to switch between using MACs and using IP addresses. It would be silly if you had to do that. So we just have a table that does that for you. Yeah. Okay. And I think, yeah, we're also going to do an nmap scan as a quick example as well. So do not do this because you might get in trouble, but I'm going to nmap a server that we have here. And if you guys have done any red team or any meetings like that, then this may have meant nothing to you, but now it should mean more, right? Or you should have like a somewhat of a better understanding. It shows you nicely all of the different components of these layers that we've gone over. So you have the IP address of the machine that you scanned. Oh, this machine has all these ports listening on it. Those ports are associated with possibly, it usually is the case that they're associated with these kinds of applications. This tells you whether, you know, that port is actually open, filtered, or not open on the host. So if there's anything that you should take away from this, then you should know what a network is, right? Specifically a computer network. You should know what a network is, or an internet, right? Or they're also sometimes called intranets. If you're like a big company, sometimes your network is so big that you call it an intranet because it's like, you know, your own private internet. You should know what IP addresses are. You should know what MAC addresses are. You should know what hosts are. You should also know what switches and routers are and how OSI layers play into all of this, right? That's it. So if you have questions, that's my Discord handle. And if you're not in the Discord, then I'm assuming everyone in here is actually, so I'm not even gonna like say that, but the link is discord.ufsit.club. That's my handle. Text me if you want to. I love answering questions, and I have more contact info on my website.